Okay, good afternoon to everyone. Is my AV is okay? Good afternoon. So is my AV is okay? Okay, thank you, Abhishek. So let us start today's class. Okay, yesterday because of some emergency meeting, so I could not continue the class. So let us take this one. So optimal scheduling of hydrothermal system. So in addition to this one, we have discussed about Kuntakar conditions for inequality constraints on dependent variables also yesterday. So we were about to discuss about optimal scheduling of hydrothermal system. So optimal scheduling of thermal system is easy task. However, when you include hydro also, because whenever you take a power system, it will not have only thermals. So it will have almost majority of them are thermal. Then the next one will be your hydro, then nuclear. Then nowadays, renewable energy sources also existing in the power system grid. So therefore, here we will consider hydrothermal system. Anyway, nuclear power plants will work on base loads. Okay, so now optimal scheduling of hydrothermal renewable energy system is the latest one. So let us not bother about that one right now. So now here we have to minimize the operating cost. So what about the operating cost for hydro power plant? Is almost negligible, isn't it? Zero. However, operating cost of thermal system we have to consider. So therefore, operating cost of hydrothermal system can be viewed as minimization of the fuel cost of your thermal plants only. However, it should be under some constraints of your hydropower plant. Understood? So earlier we have seen optimal scheduling of thermal system in which what the objective function was to minimize the total generating cost or operating cost subjected to your power balance equation. Subjected to your power balance equation we have done in model 3. Here we are taking a combination of hydro also, so hydrothermal. So because operating cost of hydro system is zero almost, so here also we will be trying to minimize the operating cost. We are trying to minimize the operating cost of thermal plants only. However, in addition to our power balance equation, we are going to get additional constraints which is based on your hydro power plant. So what are the constraints that are going to come into picture because of hydro power plant? So it is your water availability. So water availability means again it is what is the inflow into the reservoir and what is the storage capacity. That is not capacity, it is a storage. So these are the two things constraints will be coming into picture. Water availability, storage and inflow for hydro generation over a given period of time or for a given period of operation. So this hydrothermal problem is divided into two parts. One is short term, the other one is long term. Short term means it may be a day or a week. Long term may be from a month to a year. So usually this optimal scheduling will be done maximum till 1 year only. Why it cannot be done beyond 1 year? So So minimizing this one, thermal plants, sorry, I was discussing, some disturbance was there. So long term and short term I was discussing. So long term means a month to 1 year. So usually it will be done till 1 year, because for operation purpose, so it will be done till 1 year. However, it can be for planning purpose, it can be done beyond 1 year, maybe 5 years, 10 years, etc. That is your load forecasting. Load forecasting for the expansion of the existing system. So for planning purposes, so this can be done. However, here we are dealing it with respect to the operation only. So therefore, for operation purpose, so we will be dealing it with the long term till 1 year, a month to 1 year. Short term will be a day to a week. It may be from 1 day to 1 week. So we will be solving these problems. So that means that is your period of operation. It may be considered for 1 day or week or month or a year. Is it clear? So with this specified period, so we are going to minimize the fuel cost of thermal plants only. However, subjected to the additional constraints of water availability. Now let us consider a fundamental hydrothermal system. I am talking about fundamental. Understood? So fundamental means it will have one thermal plant. It will have one thermal plant and one hydro plant. Here you can see it will have only one thermal plant and one hydro plant. For explanation purpose, so we are considering it your fundamental hydrothermal system. Otherwise, if you take power system, you will have lot of thermal power plants and hydro power plants, isn't it? So majority of them are thermal plants and the other will be hydro, and also renewable energy sources and nuclear power stations also will be existing. However, so we are considering a fundamental power system, that is hydrothermal system consisting of one thermal, one hydro. Understood? And these two power plants are connected to a load demand of PD. This is your single line diagram. Understood? And because you are considering hydro plant, so obviously for hydropower plant, we should have a reservoir. We should have a reservoir where water will be stored. Where water will be stored. Understood? So that storage variable, we are considering it as X. This is X. So that storage variable, we are considering it as X. However, if you have a reservoir, so obviously there should be an inflow of water, isn't it? From where you will get the water during the rainy seasons? So what it will do? So there will be inflow will be there. Water inflow will be there, isn't it? Into the reservoir. So that water inflow variable is your J. Remember, J is your water inflow, X is your storage. Understood? And here PGT is the real power generated by thermal plant. G means generation, T means thermal plant. PGH, real power generation, G, generation by hydro plant. Okay, so this is the reservoir. Then what we are going to do? So because of this one, through your pen stock, I think you have studied in EPG, electric power generation, or UEP also, you might have studied these things, how actually the hydro power plant works, isn't it? So I'm not going to touch upon that one. So whenever you are having this one, so the water discharge will be there, obviously. Water discharge will be there. That means here you will have a turbine. So after striking the turbine blades, turbine will be coupled with your generator, isn't it? So after hitting or after striking the turbine blades, turbine starts rotating. So where the water will go, it gets discharged into the your tail race. I think you heard that one. Tail race, isn't it? So water gets discharged after passing through your turbine. So what is the water discharge? Is nothing but your output of water. That is nothing but your Q. I think from this fundamental pictorial representation, you have understood the notations here. PGT, PGH, J means water inflow. This is reservoir, storage variable X. Then discharge of water is your Q. Is it clear? So now with this simple fundamental this thing, so now let us see here. So that's what I said already. This is a fundamental one. Now here optimization will be carried out with real power generation as control variable. That means real power generation as control variable with the transmission loss accounted for by the loss formula. Understood? So here optimization we are doing, what optimization we are doing? We are considering the real power generation, that is PGI at ith bus, or just you take PG. PG is the controlled variable. What is the notation we have used in controlled variable? U. In the earlier explanation, state variable we have used it as X. Understood? Control variable we have used it as U. So here in this case, real power generation we are treating it as a control variable, and we are accounting the transmission loss also using loss formula which we have derived in the earlier classes. Is it clear? So this is your optimization problem. Now let us see what is a mathematical formulation. Mathematical formulation is the mathematical description of a physical system. Understood? Mathematical model or mathematical formulation is nothing but your mathematical description of your physical system. That is your mathematical model or mathematical formulation. Now let us see here how the mathematical formulation will be formed for a hydrothermal system. So before starting, let us consider a operational period, that is T, capital T. So this is our operational period. This operational period T may be short term or long term. That means maybe 1 day, that is 24 hours, or a week, 7 days, or a month, it may be 30 days, or a year, 365 days. So that is the thing T. Let us assume this is the operational period T. Now for this period T, it is assumed that the storage of hydro reservoir at the beginning and end of the period are specified. Clear? So with these small assumptions, we are going to represent the mathematical formulation of our fundamental hydrothermal system. What is assumed? It is assumed that the storage capacity in the reservoir of hydropower plant at the beginning will be specified, and at the end of the period it will be specified. So what is the beginning of the period is 0. What is the end period is T. So 0 comma T. 0 is initial time, T is your final time. So if you are considering 1 week, so initial stage means on the first day. So what is the storage capacity? On the 7th day, what is the storage capacity? Clear? So that will be given or specified. This is a one assumption we are making it. Now the second thing is water inflow. What is the variable we have used for water inflow? J into the reservoir. And load demand and the system are known as a function of time with complete certainty. Understood? So this is the another assumption we are making it. That is, what is the inflow water or water inflow into the reservoir? That is variable J. That is, and load demand PD on systems are known as a functions of time. That means as time varies, what is the water inflow will also varies, will not be a constant. Water inflow into the reservoir is not constant. It will change as time progresses. Clear? What happens to the load? Is it load is constant on thermal system and hydro system? Yes, nuclear power station it is constant. But here on thermal and hydro, it is not constant. It also keeps on varying. On daily basis also, you see morning load will be different, peak load will be during the afternoon, and evening, night, etc. It will vary, isn't it? So therefore, this water inflow J, variable J, and the load demand PD should be a known function of time, because these are variables with respect to time. So it should be with respect to time. With complete certainty, we should know. That is deterministic case we are going to consider. Now here you see water inflow into the reservoir. We are going to consider after considering the water which has been used for irrigation purpose. Understood? So whatever the water flow is there from through the rivers or through the hilly areas, etc., surrounding areas. So after using the water for irrigation purpose, the resultant one you have to consider it as a water inflow. Understood? So that one you have to consider it. This is the second assumption you have to make it. Okay, now let us see this one. The problem is to determine Q. Sign. Subject 17. Subject with code. So 1 second, please. Okay, and disturbances keeps on happening here. Okay, let us come back. So the problem is to determine Q here. The problem is to determine Q. What is Q? It is nothing but water outflow water or water discharge rate with respect to time, so as to minimize the cost of thermal generation. Understood? Now you understood what is the problem is to determine Q out T, that is discharge rate, water discharge rate. You have to determine Q of T so as to minimize your thermal generation cost C. That is your problem. Okay, now here I am representing it. You know how to represent the cost function, isn't it? So here over a period, why earlier we have taken only the cost function, but here we are using integral. Why we are using integral? Over a period of time. Over a period of time operation we have to do. So it will be integral 0 to t, initial time and final time. So C of t is equal to C dash of this cost function is a function of real power generation, is a cost function of real power generation of what? Thermal plant only. We are not considering hydro here. Why we are not representing hydro in the cost equation? Because operating cost of hydro power plant is almost negligible, so 0. So we are not considering it. So that's why we are considering the operating cost of thermal generation only. And obviously this real power generation is with respect to time. It will vary depending on the load. Okay, so therefore I am representing C dash of Pgt of T into dt. This is how the cost function is defined for thermal system. Even though it is hydrothermal, we are defining it cost function only for thermal. Clear? Why we are defining? Already I told the thing. So over a period of 0 to t. Now this is the cost function subjected to the constraints. Always math optimization problem means what is your objective function and what are your constraints. This is the model you have to define it. This is our objective function. Understood? So we are going to minimize this function, cost function, subjected to the constraint. That means your objective is to clear the examination. So if you want to clear the examination, you have some constraints you have to satisfy. What is that one? First constraint is your minimum internal marks you have to satisfy. Second constraint is attendance requirement, you have to satisfy 85%. These two constraints if you satisfy, then only you are going to write your main examination. Clear? Then you are going to achieve your objective function of clearing the subject. Hope you understood this one. These are your constraints. Attendance is one constraint and internal marks is your another constraints. So here also your objective function, if you want to minimize this cost function, this has to be subjected to the constraints. What is that one? Load demand. That is nothing but your power balance equation which we have considered earlier. What is the power balance equation? Generation, total generation minus losses minus demand is equal to 0. Our total generation is equal to load plus losses. This is your power balance equation. You should be in a position to say, most of the competitive examinations are in interviews also in public sector units, they will be asking what is power balance equation? Total generation is equal to total load plus losses, or otherwise you can say power balance you are telling. So therefore total generation minus losses minus load demand is equal to 0 is your power balance equation. Now here also we are writing the same equation. What is the generation? It is the generation due to thermal Pgt of T. All the variables we have to represent it with respect to T, because we are considering it operational period. So because capital T is your final time, so in between 0 and T some time will be there, T, small t I am representing it. So this is the real power generation due to thermal plus this is the real power generation due to hydro. So what is the total generation? Real power generation by thermal plus this one minus losses PLD minus demand. Only this extra term you are getting it with respect to time. Understood? Is equal to 0. This is known as your power balance equation over an interval of 0 comma t. 0 comma t. Understood? So over a period of t is equal to 0 comma t means what? Whenever brackets are shown, so it include the 0 as well as t. Understood? Suppose you know that one, isn't it? Whenever this is a bracket and here it is a parenthesis like this, if it is shown, let me take it. Okay, if I am showing it, this is a parenthesis. So I am writing it 0 comma t. Okay, small t, any variable, just this is for explanation. If this is the parenthesis on both sides, then it is between 0 to t, between 0 to t. That means you have to exclude 0 and t. You should not consider 0 and t. If it is square brackets, you have to consider this as well as this also. That means starting from 0 to t. Suppose if you are on one side, you are having it parenthesis 0 comma t, okay, with square bracket. That means what? This is parenthesis. This 0 we should not consider. But here it is bracket, so t we have to consider, till t you have to consider. Understood? Suppose if you are having bracket 0 comma t parenthesis, then this t we should not consider. So it is starting from 0, 1, 2, 3, etc. t minus, so previous interval whatever it is there, that we have to consider. Hope you know this concept. Understood? Okay. Now this is between two brackets, so we have to consider 0 as well as t with the intervals between these two. This is your power balance equation. This is the one constraint. What is the second constraint we have to consider? You see here, water flow, isn't it? So water flow, water availability you have to consider. Water availability in terms of storage and in terms of water inflow you have to consider. So let us take those constraints also. Okay. Now water availability. What is water availability? Let us see here. Storage as well as inflow. We have to consider. Now here, this is the equation which has been given it here. So directly I have written it here. So what is this one? Now let me take, this is, sorry, this is your reservoir. Okay. Now this is the water available at initial time. Available at initial time. So this is your inflow, water inflow J, and this is your water discharge Q, and this is, sorry, let me take, I am not getting it. Okay. Now what is this one? So this is your X, that is water availability output, water output, that is at time t, xt, final time. So this is the thing you are having it. So this is your reservoir, this is the water availability initially, and this is inflow, and this is discharge, and this is the output I am getting it, xt. That means this is the water head or water availability at the end of period. That means this is the water availability on first day if I am taking it weekly basis. And this is the water availability, this is the water availability at the end of 7th day. This is at first day and this is at 7th day if I am taking weekly basis. If I are taking monthly, again it will be different. So therefore, what is the availability at the end of the period T? That means at the end of first week. What is the availability equation? So this xt is equal to, what is this one? This is the first availability, isn't it? Initially, and this is the inflow. This plus this minus this one, isn't it? So that is xt, okay, is equal to, that means what is the water availability at the end of the period is equal to whatever initial water availability on the first day plus the inflow, water inflow, and obviously this is a water discharge. Water discharge means what you have to do? It is Q. This is known as water continuity equation. So from this one, so if you are taking all these constraints onto LHS side, equating to 0, this is the equation you are going to get. You see, xt, and because in order to differentiate this one, so I am considering it is x dash. That's all. The same equation only. I am considering x dash of t. What is x dash of t is this one. So I am taking x naught on LHS side. So minus x dash of 0 plus j. So I am taking it on LHS side minus j. And this water inflow will change with respect to time. So therefore, integral over a period of 0 to t with respect to dt changes with respect to time. Then this minus q is there. You take it onto LHS side, becomes plus q. And q, what is this one? Discharge. So discharge is also not constant. Water discharge will also varies with respect to time. So therefore, q of t over the integral 0 to t dt. Hope now it is clear for you. This equation is known as water continuity equation, equal to 0. This is your water availability. That means at the end of the 7th day, what is your water availability? Water availability is equal to this one. This is a simple basics. Is it clear? Any doubts? Where J of t is water inflow, already I told this one, and x dash of t is water storage, x dash of t is your water storage, and Pd is power demand, and this is a general form I given x dash of t. So therefore, x dash of capital T means it is a water storage at the end of the period t. What is a t is when t is equal to 0, x dash of 0 is nothing but water storage at the beginning. That means initial stage. And Pd is your power demand, which is a random variable. Why it is called random? The load is going to vary randomly. We cannot predict, okay, this is the load, this is the load, so it will vary. So that's why it is a random variable. Now Q is controlled variable. As I said already in the previous slide, we have to control. Q is treated as a controllable variable. What is Q? Water discharge. So Q is your water discharge, and obviously x dash of 0, x dash was specified as water storages at the beginning and the end of the optimization interval. This is the terminologies which we have used in our water continuity equation. Clear? So next, the hydro generation PGH T is a function of hydro discharge and water storage. What do you mean by water storage? Usually we measure the storage in terms of head. Hope you heard this word, head, H-E-A-D, head, isn't it? So in the penstock also you will have head, and reservoir also you will have a head. So in hydropower generation, the real power generation, we have to consider it as a function of hydro discharge and water storage. Is it clear? So this is the thing we have represented by equation. So this real power generation by hydro plant is a function, it is considered as function of your hydro discharge. What is discharge? Q of t. And what is storage? We are considering it as variable x. So x dash of t. T means it is the interval between 0 and t, capital T. Anything you can take it here. So this is how the hydropower generation can be represented as a function of discharge as well as storage. Isn't it? Obviously, hydropower generation, real power generation. So what is the available water? What is available water? Then what is the discharge output? So depending on this one, your hydropower generation will vary. Okay. Hope you understood. I am going slowly. The problem can be handled conveniently by discretization. So can be solved conveniently by discretization. What do you mean by discretization? Nowadays, earlier we used to do, there is a one language, Fortran 77, before your C language, etc. and all those things. So before Fortran 77 also there was no programs. So manually they were doing it. So now it is digitalization, isn't it? So that's why these type of problems can be handled easily by discretization. So how to discretize? Let us see here. That is, the optimization interval T is subdivided into several subintervals. Understood? So 0, T is there. So this optimization, this is known as optimization interval, is divided into several subintervals. So this number of subintervals is indicated by M. So M is number of subintervals between 0 and T. And each subinterval, what is the time length of each subinterval? It is delta T. Understood? So between each subinterval, so the time length will be delta T. Hope you understood this one. Let me show you. Now you see 0 and T. This is the 0 T, this line, sorry. Actually, this is a straight line. I am unable to draw straight line here. You assume it. This is the line. Okay. Anyway, it varies. So this is the 0, this is T. So this is divided into several subintervals like this. It is divided. So how many intervals? It is m subintervals. And what is the time length of each subinterval? That means this one. This one. Between subinterval, it is delta t. Okay. So this is your time length of each subinterval. Hope you understood this point. Now during each subinterval, it is assumed that all the variables are fixed. Understood? Each subinterval, the values are fixed. Which values? The variables which we are going to consider are assumed to be fixed for each subinterval. Okay. So now this is how we are going to discretize. How we are going to discretize is the problem. First divide the intervals 0 to t into several subintervals with a time length of each subinterval as delta t, and during each subinterval the variable values are assumed to be constant value. Now the problem is written as, now posed as, now what is this m is equal to 1 to m? This summation of PGT. What is C dash of PGT? Is your cost of real power generation of your thermal plant. But we will have several thermal plants, not only one power plant. Several power plants will have. So we have to add the cost of generating real power of all the plants. So that's why it is summation. And what is this m? It is a subinterval. Small m is your mth interval. This we are discretizing it. So it is mth interval. So where m is varied from 1 to m. What is capital M? Number of subintervals. So between 0 to t, you might have divided that one into 10 subintervals. Assume it. So this capital M value is equal to 10. Understood? Suppose m is equal to 5, small m, PGT of 5. That means this is the real power generation at 5th subinterval. Okay. So this is your cost function. However, each subinterval time length is delta t. So therefore, that has to be multiplied with delta t. Clear? So this cost function must be multiplied with your time length delta t. And we have to minimize this cost. We have to minimize this new cost. Earlier, we have not discretized. Now, after discretization, the cost function will be this one. That means discretization means we are divided into several subintervals. Now, what we have to do? We have to minimize this one, minimize the cost of real power generation minimum with respect to variable Q. With respect to variable Q. Is it clear? What is Q? Discharge rate. That is water discharge rate. That is output, outflow water. Inflow water, water outflow is there. No, water outflow is nothing but your discharge rate. Water discharge rate variable Q. Power M. M is nothing but your subinterval. So in each subinterval, you have to minimize the objective function. This objective function. Clear? Hope you don't have any confusion in this function. Minimize with respect to the variable Q. Now delta T, I am absorbing that one into C dash. Delta T, I am absorbing that one into C dash, and I am going to rewrite this one as C. What is C? C dash into delta T. I have absorbed delta T into C dash, so I am writing it as C. All other things is same. Is it clear? So we are going to minimize this new cost. This is your new cost function in discretization, under discretization. Clear? Minimize with respect to variable Q. Q is water outflow or discharge rate. Now, this is your digitized objective function. This is your digitized objective function. So we have to minimize this digitized objective function with respect to some constraint, subjected to some constraints. What's ST means here? Subjected to power balance equation. And you know what is power balance equation? What is power balance equation? PGT, real power generation by thermal plant during mth interval plus power generation by hydro plant at mth interval minus losses at mth interval minus load demand at mth interval. This is the digitized power balance equation because we got M. Earlier you see we have not specified M because we have not discretized. Now we have discretized even the cost function and the constraints also we are going to discretize. Hope you understood this power balance equation same as the earlier one. Only the thing is we are using M here to indicate that sub-interval where PGTM is thermal generation in the mth interval. All these things I have explained it. Now what is transmission loss? We have seen for two plant system because we have considered two plants, one thermal, one hydro. For two plants, already we have discussed this PL formula for two plant system, isn't it? With B coefficients. So B11, here 1, first plant we will consider it as a thermal. Second plant we will consider it as a hydropower plant. So here it is B11. So what is first plant? It is thermal. So I am writing it as BTT. Into what is the real power generated by thermal plant? PGT. At mth interval, PLM we now want, isn't it? So at mth interval whole square plus 2B12, isn't it? So there we had B12, 2 times B12. Okay, what do we have here? B12. B12 means what? Thermal as well as hydro. So therefore B thermal as well as hydro. BTH. B12 means it is 2 times B12 means BTH into PG1, PG2 for two plants we have considered in the earlier case PG1, PG2. But here PG1 means PGT, that is missing here. Please include that one here. I think it is missing here. PGT to the power of M, that is real power generation due to thermal station at mth interval into PGHM. So one term is missing here. So you can write it here. So here one term you have to write it. So that is PGT to the power of M. This term is missing, 2 BTH into PGTM into PGH. That you have to write it here. Then what happens? This is with respect to plant 1. This is with respect to plant 2. That is hydro. So that's why B22. This is B11. This is B22. This is B12. B22 means here it is hydro, HH. And what is the real power generation by hydro? PGH at mth interval whole square. Understood? Hope you understood. This is similar to your two plant quadratic equation for transmission loss, which we have considered. Okay. Now, and you know that PD is your load demand at mth interval. Load demand at mth interval. Is it clear? So this is your objective function, digitized objective function, digitized power balance equation. Now, what are the other constraints? Water constraints we have to consider for hydro, isn't it? So what are the water constraints? So that is water availability. You can see here, I'm going back. So, okay, this is the water availability, isn't it? That is water continuity equation, we have written it. But this is before discretization. Now the same equation we have to write it after discretization. After discretization. Is it clear? This equation we have to represent it. Now what you have to do, just for your reference, now it is time up already, just few seconds I will take. This is a digitized or discretized objective function. This is a discretized power balance equation. Then discretized water balance equation you represent. Then after representing the discretized water balance equation, so what you have to do, you got a mathematical model or mathematical formulation. Then for this mathematical formulation, you have to apply the necessary conditions. First step is obtain optimization problem, optimization model. That is nothing but your mathematical formulation or mathematical model. Then obtain the necessary condition. How to get the necessary condition? By applying Huntaker conditions. Then you are going to get the solution, necessary condition. This is the procedure we are following for any optimization problem. First, you get an optimization model, define necessary conditions, then you get the solution. Necessary condition is through Huntaker conditions. Hope you don't have any doubts till this point. All the terminologies, equations which I have used it, I think it is clear to you now. If you have any doubts, you can ask me. Otherwise, we will end the class. We will go for lunch. Any doubts? Hope you don't have any doubts. Okay, thank you one and all. Take care.